Hello students, in this video we will study about two colligative properties, boiling point elevation and freezing point depression. Let us first consider boiling point elevation. The boiling point of a liquid is the temperature at which its vapor pressure becomes equal to the atmospheric pressure. It is found that boiling point of a solution is always greater than that of the pure liquid. The increase in the boiling point of the solvent when a non-volatile solute is dissolved in it is called elevation of boiling point, and it is denoted by delta Tb. Let Tb naught with the boiling point of pure solvent and Tb with the boiling point of solution. Then delta Tb is equal to Tb minus Tb naught. Let us try to understand elevation of boiling point with the help of a graph of vapor pressure versus temperature. The vapor pressure of a solvent and solution increase with increase in temperature. The temperature at which vapor pressure of solvent becomes equal to atmospheric pressure is the boiling point of solvent Tb naught. And the temperature at which vapor pressure of solution reaches the atmospheric pressure is the boiling point of solution Tb. The difference between Tb and Tb naught is called elevation of boiling point. We know that vapor pressure of a solvent decreases due to addition of a non-volatile solute. Thus, vapor pressure of a solution is always lower than that of the pure solvent, and vapor pressure increases with increase in temperature. Hence, the solution has to be heated more to make its vapor pressure equal to the atmospheric pressure. Let us now study the relationship between elevation of boiling point and concentration of a solution. Experimentally, it has been found that elevation of boiling point delta Tb is directly proportional to m, where m is the molality of the solution. Therefore, delta Tb is equal to Kb into m, where Kb is a constant of proportionality which is called molar elevation constant or boiling point elevation constant or ebullioscopic constant. If molality of the solution is 1, delta Tb is equal to Kb. Hence, ebullioscopic constant Kb is defined as the elevation of boiling point produced by 1 molar solution. Units of Kb will be equal to unit of delta Tb upon unit of m. Unit of delta Tb is Kelvin and molality has the unit mole per kg. Therefore, unit of Kb is equal to Kelvin kg per mole. The experimental determination of boiling point of a solvent and solution and thus boiling point elevation can be used to determine molar mass of a solute. According to equation 1, delta Tb is equal to Kb into m. Let W2 and W1 be the mass of solute and solvent in gram respectively and M2 be the molar mass of solute in gram. Molality M is equal to number of moles of solute divided by mass of solvent in kg. 1 kg is equal to 1000 gram. Therefore, molality is equal to moles of solute in 1000 divided by mass of solvent in gram. Number of moles of solute is equal to mass of solute in gram divided by molar mass of solute in gram per mole. This is equal to W2 upon M2. Therefore, delta Tb is equal to Kb into mass of solute in gram divided by molar mass of solute in gram into 1000 upon mass of solvent in gram. Therefore, delta Tb is equal to Kb into W2 into 1000 divided by M2 into W1. Let us write the equation in terms of M2. Therefore, M2 is equal to Kb into W2 into 1000 divided by delta Tb into W1. If we know all the other quantities, molar mass of solute M2 can be calculated. In cold countries, during winter season, the roads and footpaths get covered with the snow due to heavy snowfall. Let us see how the next colligative property, freezing point depression, helps to remove the snow from the roads. The temperature at which vapor pressure of a liquid becomes equal to vapor pressure of its solid phase is called freezing point. It is found that freezing point of a solution is always lower than that of the pure liquid. The decrease in the freezing point of the solvent when a non-volatile solute is dissolved in it is called depression in freezing point. It is denoted by delta Tf. Let Tf naught be the freezing point of pure solvent and Tf be the freezing point of solution. Then the depression in freezing point, that is delta Tf, is equal to Tf naught minus Tf. Let us now understand depression of freezing point with the help of a graph of vapor pressure versus temperature. The graph shows three curves. CD is the vapor pressure curve of liquid solvent, EF is the vapor pressure curve of solution, and AB is the vapor pressure curve of solid solvent. The curves AB and CD intersect at point B. Thus, the solid and liquid phases are in equilibrium at point B. The temperature corresponding to B is the freezing point of solvent, Tf naught. Similarly, the curves AB and EF intersect at point E. Thus, the solid solvent and solution are in equilibrium at E. The temperature corresponding to E is the freezing point of solution, Tf. The difference between Tf and Tf naught is called depression in freezing point. Vapor pressure of the solution is lower than that of the pure solvent, and hence solution curve meets the vapor pressure curve of a solid solvent at a lower temperature. So the solution freezes at a lower temperature than the pure solvent. It is important to note that the solute does not dissolve in solid solvent. Let us now study the relationship between freezing point depression and concentration of a solution. Experimentally, it has been found that the depression in freezing point delta Tf is directly proportional to molality of the solution, which is denoted by m. Therefore, delta Tf is equal to Kf into m, where Kf is a constant of proportionality, which is called freezing point depression constant or cryoscopic constant. If molality of the solution is 1, then delta Tf is equal to Kf. Hence, cryoscopic constant Kf is defined as the depression of freezing point produced by 1 molar solution. Units of K will be equal to unit of delta Tf upon unit of m. Unit of delta Tf is Kelvin and unit of molality is mole per kg. Therefore, the unit of Kf is Kelvin kg per mole. The experimental determination of freezing point of a pure solvent and solution, and thus depression of freezing point, is used to determine molar mass of a solute. According to equation 1, delta Tf is equal to Kf into m. Let W2 and W1 be the mass of solute and solvent in gram respectively, and M2 be the molar mass of solute in gram. Molality M is equal to number of moles of solute divided by mass of solvent in kg. Therefore, M is equal to moles of solute into 1000 divided by mass of solvent in gram. Number of moles of solute is given by the formula mass of solute in gram divided by molar mass of solute in gram per mole. Therefore, number of moles is equal to W2 upon M2. Substituting in equation 1, delta TF is equal to Kf into mass of solute divided by molar mass of solute into 1000 upon mass of solvent in gram. Therefore, delta TF is equal to Kf into W2 into 1000 divided by M2 into W1. Let us write the equation in terms of M2. Therefore, M2 is equal to Kf into W2 into 1000 divided by delta TF into W1. By knowing all the other quantities, the molar mass of solute M2 can be calculated. In cold countries, ice frozen on roads and footpaths is melted by spraying salts like sodium chloride or calcium chloride. Ice melts into water as the salt depresses the freezing point of water. Ethylene glycol is a common automobile antifreezer. It is water soluble and non-volatile. Ice and salt is used as a freezing mixture to make ice cream in ice cream pots. Is this video helpful to understand these colligative properties? Please let me know. Thank you.